let's welcome Danya Muhamad from Canada.
Perfect. Thank you. All right. Hello. My name is Danya, and the project I'm going to talk to you about is titled Environmental Quantum Laser Ranging. And this is a project I did at KTH with the Quantum Nanophotonics group, specifically Dr. Val Zwiller and Dr. Art Branney. So I got involved in this project in a fairly typical way. I was actually interested in quantum communication, and I contacted Val asking if he had any projects that he knew about. And as you can clearly tell by the title of my presentation here, that clearly didn't pan out. But he did put me in touch with his postdoc, Art, who mentioned the idea of quantum laser ranging. And that was really interesting because I have a background in radar. And it's been a great experience so far, so I would really recommend taking initiative and being open to new ideas. So why do we want to monitor pollutants? Well, pollution is a worldwide problem affecting everybody on this planet. And 90% of the world's population is living in areas where the air quality is reaching harmful levels. As a result, there are a lot of well-known, dedicated international bodies that are interested in monitoring air pollution, such as NASA, IPCC, and WHO. The way that CO2 is currently monitored does not yet yield live 3D images. This is because we only measure at a few specific points per day, and we produce images like the one here that are 2D. And the reason why this is lacking is that we miss a lot of short-term emissions, like in cities. And cities account for 70% of the overall CO2 emissions. And this is an important factor when we consider how carbon is moving within our environment. We need better data with better resolution for two reasons. The first is that better information about our air quality allows us to make better policies to regulate emissions. And the second is that it helps us to improve our climate change model, which right now has huge error bars. So to bridge the current knowledge gap, the project I worked on looked at using LiDAR. So what is LiDAR? LiDAR, which is short for light detection and ranging, actually operates using the same principles as radar, except instead of using a radio wave, we use a light pulse from a pulse laser. So this, oh, my bad. So if you look at the figure, we start with the pulse laser, which emits a light pulse, which then hits a target over here. Oh. Okay. So we hit a target, and that light can be either scattered or absorbed. And then the backscattered pulse is received by the detector. And information about both the time and also the intensity is then used to gauge both the distance and represent it in a 3D point cloud. Application areas of LiDAR include autonomous vehicles, agriculture, forestry, and many more. So the project I worked on focused on developing a prototype LiDAR for atmospheric remote gas sensing. So how that works is that if you look at this figure, each gas has its own absorption spectrum, and it more strongly absorbs at certain wavelengths than others. To sense gases in LiDAR, let's look at this example, where we have two gas plumes, one closer with a reduced concentration, and one farther away with a stronger concentration. So we use a pulse that's on resonance, so at a wavelength where there's strong absorption, and one off resonance, where there is low absorption. So at the first gas plume, the on resonance wavelength. Okay, so the light from the laser hits this first target, and it is absorbed, and so we see a drop in the signal, which is represented by these two regions. And then we also use one that's off resonance. And then the subtraction of the two gives us a signal that is proportional to the concentration of the CO2 gas. So the problem with current LiDARs is that they use detectors that operate at 1.6 microns or below. And this is a problem when we look at using it for gas detection, because most greenhouse gases have higher absorption peaks at above 2 microns in wavelength, as you can see here. A detector that does allow us to use to operate at 2 microns and above is superconducting nanowire single photon detectors. And this is why we looked at integrating them into the LiDAR that we use for atmospheric remote gas sensing, as it improves the sensitivity. So the quantum nature of this project is really in that we are able to measure single photons. And single photons are what compose light, and they're the smallest unit of light, and that's why they are a quanta of light. With this technology, a single photon of light is capable of generating a strong enough signal to be detected. And the images here are for context about the actual size of the detectors. So here in the bottom is the fully packaged detector, and over there is the actual nanowires within that detector. And they're arranged in a snake-like pattern up in the top. So if you're curious to know more about superconductivity, the operating principles of the detector, or about the scanning and the creation of the 3D maps, which is what I was mostly involved in, I invite you to come see me at my poster afterwards. And I'd like to end my presentation with some general advice. You don't need to have a concrete idea about exactly what you want to do or how you can contribute. Research is a collaborative process, and so don't hesitate to contact your professors and teachers, and together find ways to contribute.
Thank you very much. Do we have some questions? No question? Okay, then everything was super clear. All right. So, thank you again.